includes the fracture mechanics of concrete, concrete and rock, the nonlinear behavior of a cement-based material, high-strength concrete, fiber-reinforced and self-combating concrete, sustainability and effective use of chemical admixtures. And he is a recipient of many honors and awards. To mention a few, he is a fellow of Indian National Academy of Engineering and president and fellow of ILM, International Union of Laboratories and Experts in Construction Materials, Structure and Systems, based in France. And he is in the editorial board of many international journals. He is involved in more than 70 R&D research, R&D funded projects. And he has more than 500 publications to his credit, which includes some 25 book chapters, and he has guided more than 21 on PhD research projects. It's a great pleasure, sir, inviting you to this session. Now the session is yours, please.
Thank you. Thank you very much. Thank you to the organizers for having me here. So I'll share my presentation and go on. Is my screen visible?
Yes, sir.
So I'll talk a little bit about design of textile reinforced concrete, focusing on sustainability. We have a large group working with us, and you see some of the names here of students and postdocs who are involved in this research at IIT Madras. So basically, it is a relatively new area for us and for Indian researchers. We believe that this is going to help in terms of sustainability, and that is why we are putting a lot of effort into textile reinforced concrete. So this is part of work that we are doing within our group called Technologies for Low Carbon and Lean Construction. So this is a group involving about 30 researchers, faculty members, a large group of PhD students and research scholars who are working together to promote technologies for low carbon, that is low environmental impact and less wastage, is what we call lean construction. So talking about sustainability, sustainability goes much beyond just the carbon footprint. It is a good idea, or it's a good beginning to look at the Sustainable Development Goals of the United Nations. 17 goals were put together in 2017, and these are shown here on my screen. Deals with aspects that affect every human being. Each one of us is affected by the goals 1 to 6, like poverty, hunger, health, education, gender equality, clean water and sanitation. The next row talks more about groups of people, communities, villages, towns and cities and countries, like energy, work and growth, industry, infrastructure, reduce inequalities, sustainable cities and communities, responsible consumption and production. The last row, 13 to 17, talks about what is important for the whole planet, all of us. So any action taken in any place will affect all of us in these ways, like climate action, life on land and water, peace, justice, and strong institutions and partnerships for these goals. So I think this is a good way to look at sustainability instead of just looking at environmental impact that we often do. So I want to emphasize that sustainability is much more than just carbon. We have to keep all this in mind. Similarly, construction is much more than making the structure. We put in a lot of emphasis in design, but there is much more to it. And design nowadays is basically automated. So design takes the back seat when we are talking about sustainability. We have to bring in other aspects to design for. So some of these aspects which are relevant or some of the SDGs, Sustainable Development Goals, that are relevant to us are what we have listed here. Industry, innovation, infrastructure, we can play a very important role. Similarly, in sustainable cities and communities, responsible consumption, production, climate action, and life on land. These are some aspects where whatever we do in construction affects directly these sustainable development goals and can help or damage the way that we are approaching the sustainability. So when we are talking about construction materials, construction systems, we can look at the three pillars to categorize, classify what we are looking at. Of course, there is the environmental part where we are looking at global warming, making sure that the elements and the materials we use are not affecting the greenhouse gases. Water is something that we have to worry about, especially in India. A lot of our construction systems require a lot of water, especially when you're using concrete. And therefore, we compete with people who are fighting for drinking water when we are looking at water for construction. Similarly, energy, raw material, all these aspects directly affect the environment. Then we have the social aspects. Housing is still a big concern. We should work towards faster, better, and quality construction. Our infrastructure is aging, so we will have to repair. There is a limit to how much we can build, and we have to start repairing and reusing. And most importantly is the economic. We have to extend our real estate. We have to make sure our maintenance costs are minimum and reduce transportation costs. So these are aspects which are very important. If we forget, do not involve the economic aspect, then our technologies, whatever we can invent, will not be useful to anyone or nobody will use it. So these are things that we have to keep in mind when we propose something new, when we propose a system that has to be adopted, and if we want industry to take us seriously. So we believe that efficient and economic construction can happen with this textile reinforced concrete. We can reduce carbon emissions, go for more durable structures, and maybe look at reuse and recycling as well as leading to sustainability. For sustainability, again, we have to think about the life cycle of concrete. We have to look at all aspects which are important. We have to look at the products, emission, and waste occurring in different segments, different stages of its life, starting from cement production. We all know that cement production is energy intensive and carbon emissions intensive because of the process of making cement. It requires limestone to be converted from calcium carbonate to calcium oxide, and we have to burn a lot of fuel to heat it in the kiln. So if we can work on this aspect, lot of help can be done for the environment. Then we have the concrete. We use a lot of raw materials. We should remember that 70% of our concrete is made out of aggregates. And for aggregates, we are digging up the mountains, we are digging up quarries. And if we can recycle instead of using pristine aggregates, we'll be doing everybody a big favor. Then the construction is where we go for lean construction. We want to reduce waste not only in materials, but also in energy, productivity, people, and material. Finally, we have to see if we can extend the service life. That is where durability becomes very important. I believe that we cannot talk about sustainability without keeping durability in mind. And as far as concrete construction, I think that is the most important thing. And we have to remember durability before we can think of end of life and demolition and so on. So for me, durability is very, very important. And before we come to the end of life, because demolition and reuse of concrete is always very complicated. For this, we have to know what is the electricity being consumed, how much power we are consuming, how much water also. So this gives the full picture of the life cycle of concrete and all the different aspects that we have to take into account or at least keep in mind when we are talking about sustainability. So how does textile reinforced concrete fit in? So textile reinforced concrete uses a fine grain matrix. It uses aggregates of maybe 2 millimeters or less. And we use non-metallic reinforcement, carbon and glass. Mostly now glass is used, say AR glass, alkali resistant glass. We are working on E-glass also. And we get this textile reinforced composite. So because we use non-metallic reinforcement, corrosion is not a concern. We optimize the material. We can make the material to give us the strength that we want, the permeability that we want. We have a lot of freedom, therefore, in the design. And since we put the reinforcement in layers, we can have multiple layers. We can have layers where we want. So that gives us more flexibility. Therefore, what we see is that we can optimize the section size. We can save material, lower dead weight overall in the structure, better durability, shrinkage and crack resistance, so we can go to thinner elements. And since we are decreasing volumes, the transportation costs also decrease, and therefore the carbon footprint decreases. So this is the context of the textile reinforced concrete. So let me start a little bit on the binder. What are the types of binders we can use and how we can work on the binders themselves? So in order to do this, we have to study cement process. This looks very complicated, and there are many studies where we also have explained how this is done. So this is a process flow and a material flow for cement. We, especially in a country like India, we have a variety of ways that cement is made, and how to decrease the carbon footprint can only be done when you study this. So this is for a particular plant that one of my students, Anusha, worked on. And you see here the process of making the clinker. We need electricity. Electricity can come from different sources. On the top left, you see different possible sources. Each has a different carbon footprint. This electricity is used in this whole process. Then we have the raw material. So raw material is not only limestone. Most cement companies now have been using alternative materials also. And here in this particular case, you see laterite being used, red mud being used to get the mix along with the limestone. Limestone is the primary material, but there are other materials also coming in. And you will see that each time we are looking at a material, we're also looking at how many kilometers it is traveling, because that is also carbon footprint. We are using diesel for transportation, so that is also important. Then we need fuel for calcining, for clinkering. And again, here, it is not just coal. Often in India, we use pet coke and we use other waste materials. So alternative fuels are used extensively in Indian cement plants, and we have to take that into account. All this is mixed together, heated to get the clinker. Then the clinker is mixed with gypsum in the ball mill, crushed, and we get ordinary Portland cement. And if you do all this process, you can come up with some numbers. At the bottom here, you can see that the carbon footprint in this particular case of 1 ton of ordinary Portland cement is 855 kgs. It requires 3,900 megajoules per ton of cement. Now, the same cement, instead of it being OPC, was PSC, Portland slag cement, where we are using granulated blast furnace slag, ground granulated blast furnace slag, and we truck it in, grind it and mix it in. We see immediately the carbon footprint decreases a lot. We go down from 850 to about 500. So that is the first thing we should do. We should make sure that there is less clinker in our concrete and cement and concrete. We should make sure that we're using as much waste as possible, and we should quantify. Just because we use waste doesn't mean that everything decreases and everything becomes nice. We have to make sure that we know how much is decreasing. So we start off with a binder that is helpful in terms of the environment, in terms of sustainability. And again, for this particular case of the cement plant in Nandyal, you can see in the chart below what are my carbon footprints for the different types of cements. OPC, as I said, most of the problem is due to clinkerization, 850 kg of CO2 per ton of cement. This comes down in PPC, Portland Pozzolana cement. On the table at the top, you see the different values that we have for the composition. Portland slag cement is much less. LC3 is a new cement that we are working on. This has limestone calcine clay, replacing about 50% of the clinker. So there is a lot of research going on, particularly at IIT Madras. Professor Manu Santhanam, my colleague, is leading this initiative, where 30% calcine kaolinitic clay is mixed with about 15% of limestone powder to substitute the clinker. And this also helps a lot in bringing down the carbon footprint, especially if you don't have fly ash in the vicinity or if you don't have slag. So the starting point has to be a good binder. We have to have a binder that has a low carbon footprint, low energy, embodied energy, available easily to make our textile reinforced concrete. Then once we have this, we can go for the design of the textile reinforced concrete. So on the left picture, you have a cross section of textile reinforced concrete, layers of reinforcement that can be used to make, for example, a treatment plant, a modular treatment plant that I'll come back and discuss later. So first is the material selection. We have to know what is the fabric. So these are fabrics that are locally available, internationally available. We have to select them based on the strength, the stiffness, durability, and the economy. The matrix, as I said, the starting point could be a sustainable binder. We have to design for strength, stiffness, bond, and protect the steel and economy. Then we look at the mechanical response. We see what textile configuration will work best. We look at the tensile stress strain response, because this element is basically working under tension. It is like a thin element working under tension. There will be some compression, shear, and so on, but primarily we are using the textile to increase the tensile properties. Then we identify what are the design parameters. We have looked at what we call an efficiency factor. We have to have models which lead us to the design. The structural design comes in at the end. We look at the moment capacity, minimum reinforcement, and so on, just like we would do any other structural design. Okay. So next, let me look at the mechanical response. This is what happens when you test a panel of textile reinforced concrete. These are images from digital image correlation of one of my students, Ramakrishna, who's just finishing this work, where you see that as the uncracked element is loaded, there is first a crack which is occurring somewhere at a weak section. Then the textile starts to bridge. Once the textile starts to bridge, that section no longer is weak. So some other section breaks. So you end up with multiple thin cracks, and you have like a plastic plateau. You get a plateau or you get hardening. So this is what we are aiming for. We are aiming for a material which is not softening. It is plastic, ductile, and hardening. So our load carrying capacity keeps increasing, and you see the multiple cracks. Lot of cracks occur instead of a one single crack in this phase. So this is what we are looking at. Ultimately, there will be failure somewhere, but that will be much later, very high strain. So this is the behavior that we want. We are looking at different ways of testing because we have to understand how to test it. So even the end conditions matter, as is shown here. So we have the panel with a fixed grip where we are fixing both the ends and then pulling, or we are rotating. We are allowing for rotation. That is what we call a pin grip or a rotating grip. What we have found is, after a lot of research, we are able to get both of them systematically, but there are some changes. For example, in the fixed grip, what happens is as you pull, the specimen has to accommodate the change in the load direction. So there is some random cracking, some inclined cracks. Whereas when the load is centered in the rotating grip, we have very sequential and systematic cracking. And if we design properly, you see that after the first crack, the load keeps on increasing. There is no plastification and there is an increase. And these are the images or when cracks start. Each drop signifies a new crack. Overall, the material is hardening type behavior. So now we can design for hardening type response, and failure need not occur at very small strains like we do for normal concrete or fiber reinforced concrete. And we have now a system which is behaving as a strain hardening material. The same effect we see when we increase the number of fabric layers. Instead of going with few layers, if you increase the number of layers, you see that it becomes more and more bilinear. There is a transition from softening to trilinear to bilinear. So this is what we believe is an ideal material behavior. So we design the material such that you will have a response like this. So we put the number of layers in order to get this. So we get a behavior like this. So this is what we are aiming for. There are other things also which matter. For example, how to put the layers. If you put all the 4 layers together, you find that the response is different. You get less load because what happens is the layers start sliding on each other. So it is better to put layers with spacing less, like we would do for reinforced concrete. Better to have layers and not all bundled together, so that slip is avoided. So these are things that we have been learning as we go along. Also, we can see how to increase the initial cracking. The first crack depends on the matrix. But what we found is that if we add glass fibers or we have close knitted textile, then the first crack goes up. Otherwise, it's mostly the binder behavior, the matrix behavior. But what we have seen is that if we add a few glass fibers or we make the textile architecture slightly different, then the initial load carrying capacity increases. So that means the first crack is delayed or it occurs at a higher load. So we can influence also the first crack by this type of behavior. The coating also matters. All textiles are coated. You do not have textiles without coating because it's difficult to do the weaving and it's difficult to do the placing. So all textiles are basically coated. They are coated with epoxy or styrene butadiene rubber, and depends on the coating. The efficiency depends on the coating. So here I have 2 cases where you have a textile yarn. This is a textile yarn. If you see the scale bar, this is about 1 or 2 millimeters. And you can see that here, this is fully impregnated. That means the coating or the coating material has fully impregnated the fiber. Here you see that in the bottom, in the F1 yarn, you see that the coating is only on the outside. Inside are loose fibers. So when we are pulling, this becomes more efficient. You see here that we are able to mobilize about 60% of the tensile strength of the fiber within the composite. Whereas here we are only able to mobilize 40%. So the type of coating, how the material textile is manufactured means a lot. So it is not same. Any textile is not the same. This is very, very important to understand that people should not just say, okay, we know textile reinforced concrete works and we use any textile. It will not work. So we have to be careful about all this. So the type of coating matters. And here again, you see the effect of coating. You see that epoxy coated works better. Mostly it's epoxy coated. SBR coating also has been used. So we have to know the difference. We cannot throw away one saying it's bad or good. There are some advantages to SBR coating also, and I think it's cheaper. So the coating also matters in terms of the response, and we should know how to do it. Now we have to, when we do an element, we have to overlap the textile, just like we do splicing and lapping of reinforcement. So we did a lot of tests with different overlap lengths. This was done by my postdoc Komati, where she was looking at different lengths. And we found that if we have about 150 mm lap length, it was good enough. So that means when you have a long element, you should make sure that the textile is overlapping at least 450 millimeters. Yeah, that becomes like a overlap that will transfer the loads and stresses. So just like we would have a splice, just like we would have an overlap length in reinforcement, we have to look at the textile reinforced concrete also with the lap length. More important is the glass textile durability. This has been studied from the 80s. This is work that I'm showing of Mubashir and Shah later, Professor Shah later in the 1990s, where they found that the textile can be attacked by the cement matrix. So we have been working a lot on this to see how to improve the durability. So again, due to aging or the textile within the concrete, there is a lot of loss in load carrying capacity. And this we can explain looking at this. So here I have values of tensile strength or the peak tensile stress going down due to exposure to different solutions. Here we have different solutions, but with different pH values, simulating what could happen in cementitious binder. We find that if it's AR glass, alkali resistance glass, then really nothing happens. The textile behaves quite well. However, when we have E-glass, which is a cheaper glass, a more common glass, we find that this is the strength loss is occurring. And if you look at it carefully, you see that the E-glass, instead of being like this, like in the top image, starts to have pitting. And there is something like corrosion which is occurring where the glass is degrading. This is what we want to prevent. We want to use E-glass as much as possible because it's a cheaper glass, it's a more common glass, but we also want to make it more efficient. So this is what we are working on. And so we want to have a behavior similar to AR glass in the E-glass also. So we have some loss in behavior, but we are trying to change the binder. So this is a more efficient binder, lower water binder ratio with fly ash, and we see that already we are approaching the behavior in AR glass, though we have to improve more things. So basically what we are doing is taking E-glass, which is a cheaper glass, and modifying the binder so that we can get better behavior and less durability problem. So this is what a major part of our research is focusing on. So first we have to choose the binder. We look at a binder for sustainability, strength, and so on. Then we look at the appropriate textile. So in the textile, we have to choose what is the material. Is it glass or carbon? How are we coating it? And what is the architecture? We have to do tests on composites to make sure that you have a bilinear behavior. We want a strain hardening type behavior, not a strain softening type behavior. So it's very important to know how many layers we are putting together. Then the durability comes in. We want to protect the glass textile so that there is no attack because of the binder. And this we can look at it in different ways. We have done some microstructure studies where we are looking at the defects in the coating which promote the attack. So a lot of times we see that the coating, even instead of being uniform, has some defects, and the alkaline solution penetrates and attacks. Also, depending on how the textile is made, we can have some parts which do not have much coating because the yarns are bundled and later coated. And we find that in some places the coating does not penetrate, and you have this linear corrosion, linear type pitting which occurs in these regions. So in a region like this, you can have this pitting corrosion along the line. So it's similar to corrosion of steel, but this is corrosion in glass because of the attacks. And the coating sometimes does not help much. So the type of coating matters a lot. So we are working on the type of coating. We are seeing how the coating thickness matters and so on. Also, when we are talking about AR glass, there are a lot of alkali resistant glass in the Indian market, which really are not alkali resistant. There are many people who are selling what they call alkali resistant textile, which is not true. The true alkali resistant glass has to have zirconium. It has to have about 10 to 15% of zirconium, but there are others in the market which have almost nothing. We have found some which only have zirconium in the surface or very low zirconium content. And when we analyze this, you see this pitfall. And when the pit forms, then at this place, there is a very high stress concentration and then there is failure here. So we have to be careful when you buy something thinking it's alkali resistant glass, it may not actually be so. Okay, so this is about the material. Now we have to go to the structural design and we have to see how do we design something. So we can start with existing literature. There's a lot of work done by Professor Mobashir in Arizona State, where he takes the stress strain behavior of the composite. This is what I showed you before. Like you have a bilinear behavior, we have experimental data, and then you idealize with a model. You take a model and say that this is something that we can use as the constitutive behavior, and then go on to predict what happens, say, in bending. So we have used their methodology and their model, and we predict the experimental behavior. And you see that you get a reasonable fit. Right now it is on the upper bound, but we have to work on it a little bit more. The light gray curves are experimental curves, and this top one is the prediction made from this. So we do a tension test, get the model, and use the tension test to predict what happens in bending or some other element. So we've been progressing a lot here. Now to larger elements, we can use yield line analysis. The textile is going to help in the rotation capacity. And we know that when there is rotation possible, we can use yield line analysis. So if you have a slab such as this, we can derive the rotation capacity. We can look at the moment capacity, and even in, say, circular slabs. So we can use similar concept to yield line for textile reinforced concrete also. So this has been done by many people, and we are also finding that it is quite useful to do it. So I started off with the binder, textile, coating of textile, putting it together, and looking at durability. Now you have the material, and there are ways to do the structural design. So yield line analysis is a way. Then I showed other ways that we can use some solutions coming from the tensile behavior to the structural behavior. With all this, we are confident that we can make elements, we can make structural elements with textile reinforced concrete. And for those of you who have been around for a long time, you will recognize that there is a similarity between this and ferrocement. Long back in the 1960s and 70s, ferrocement was very big. But ferrocement could not be used extensively because of corrosion. And we had to live with metallic reinforcement meshes. Here, we are doing something very similar, except that you are using glass or carbon as the reinforcement instead of metal. Otherwise, the situation is very similar. Other differences are now we have coatings, we have to worry about coatings, we have to worry about spacing and so on, so which come into the picture. But overall, the concept is very similar to ferrocement. Obviously, we are not using steel, so you don't have the ductility of the reinforcement. Glass continues to be a brittle material. It will have failure. But playing with the architecture, playing with the different number of layers, we are able to get the behavior that we want. So if you do this, there are many applications which can be done. There are a lot of applications have been done in Germany, like what you're seeing, a thin roof was built. You can see all the people who designed it on the roof. There was a segmental bridge also that was done. So these are elements. This is a curved section made out of segments and then pre-stressed, made out of textile reinforced concrete. This was an experimental bridge. In India also, there are places where we are having thin elements. These are facade elements in Mumbai, which have been done. At IIT Madras, we've been working extensively. So we've been making modular tanks that, again, like we used to do with ferrocement, segmental tanks where we make for segments that can be put together at the site to make a tank or a deposit or a box. And then we can also use in strengthening. Here you see some column strengthening that we have done at IIT Madras, where we had a column which had severe corrosion. It had to be repaired. And instead of FRP, we decided that we will go for TRC reinforcement. So here you see the textile being placed. Then there is a laying up process, which a regular mason can do, and you can build up. Decide, depending on the number of layers you want, you can build up. with this type of fiber. In this particular case, it's an epoxy coated textile. So more things can be done. Here, this is an element where we have tried to bend in the fresh state. So if you want, say, a stormwater drain section, or you want to make some bench like this, what we have done is you make a mold like this, pour the concrete, and then when the concrete is fresh, you make sure that the mold can bend. So then you get the section that you want. And then you finish it off and you can do this. So this means that we can prefabricate elements like this by appropriately engineering the mold and using the mold to give you the element you want. Other cases we can think of are textiles which are three-dimensional. Instead of multiple layers, we can have like a cage, just like we do for reinforcement in prefabrication. So what we did is we took multiple layers and put spacer yarns. So we made this 3D textile by ourselves with multiple layers. And then once you have it, then we can just insert it into a mold. It could be circular, it could be square or planar. And then we can pour the matrix in. So you have to have a flowable binder that will penetrate. This is very important to know that we should have the binder or the matrix that can flow between the yarns. Otherwise, you will not get good bonding. There'll be failure due to pull off, and there'll be slipping. So the challenge in making the binder is a binder that can flow, can penetrate into all these yarns, so that the bond is very good. If you don't have bond, then you will have slip failure. So this is very, very important. Making the reinforcement and also making the appropriate binder is very, very important. So we think the future could be with this type of textiles, textile meshes, which can be prefabricated and put into practice here. So this is how it's done. So you have a 3D textile, not layer by layer and laying up, and then you insert it into the mold, and then you can get the element. Similarly, we are doing it also for a ring. So you can have the reinforcement made, prefabricated, put it in, and then you pour the binder inside to get your element, and you get something that is properly, very neatly done. And we can use this for different elements. Here we are using it for tanks, but other things are also possible. So to summarize, we can go for sustainable design of textile reinforced concrete structures. We have to look at different things. The mechanical obviously is very, very important. Eco-friendliness is important, and durability. When we are talking about sustainability, all these three become very, very important in addition to cost. And from our research, we seem to understand how to modify the behavior to go from trilinear to bilinear at high reinforcement ratios, and we prefer this for the structural performance. We don't want the curve, the stress strain curve, to drop or even flatten. We want a rising curve because that, we believe, makes the system more efficient. If we want to use the first crack load, we can use close yarn spacing and microfibers. We have defined an efficiency factor which is independent of the volume fraction or the number of layers. So once we do the test, we don't have to keep on repeating the test for number of layers. With this, with certain number of tests, we can get the efficiency. The e-glass is something we have to work on. It is cheaper, it is more readily available. So if we can reduce the degradation, we know that there is degradation. We have determined it under accelerated aging. But if we can show that we can find a way to stall the degradation, slow down, that would really help. And the extent depends on many things like textile coating and fibers and so on. So a lot of our work is done within the framework of an Indo-German project, where we are looking at modular, lightweight waste treatment plants for rural and peri-urban areas. We are working together with